The third major step in this OpenCL program is kernel compilation. Now, I want to show you here a very simple compilation process for FPGA devices. And keep in mind that we will see quite different things for FPGAs in terms of the kernel compilation. Because for FPGAs, we have to do compilation offline. So it's a little bit different from what we see here. In this example, we'll assume that the program source, the source code in the kernel.cl file is stored in some variable already. And typically the host will allocate a character buffer or character array to store all the source code that read from this kernel source file. So we'll call this CL create program with source. And CTX is context that you have been created. One is the default parameter, which we'll talk about later. And here is the pointer to the source code. And also it has another default parameter argument to this call and the return value. Once we create this program, then we need to build the program. Build the program is essentially the way to compile the OpenCL source code into binary. So what we do here is we call this API CL build program. My program is the one you just created, and also along with some default arguments. And this CL build program will return success or failure, depends on the compilation result. Now, the compilation is done on the whole kernel source code because kernel source code may contain multiple kernel functions. So the next step is to create a kernel by selecting the right kernel function from that source code. So because you may have multiply function, kernel function, addition kernel function, or other kernel functions in the same .cl program. With compilation, you can have all the entry point to these different kernel functions. So this CL create kernel is to really select the right entry point for the specific kernel function you choose to use. And the input argument is the my program, which was created ahead of time. And the second argument is the kernel function name that you choose to use. The fourth major step is to run the kernel program. Now, before we run the kernel program, we have to initial the kernel arguments properly. When we design any kernel function, we will typically have some number of kernel arguments. And we will do this kernel arguments initialization in this way in the host side. On the host program, which we're seeing here, we use CL set kernel argument. This is an OpenCL API. The first argument to this call is the kernel that you just created using CL create kernel API call. And then you use a number to indicate which kernel argument you're trying to initialize. Following that, you will specify the size of the kernel argument and then the actual value of the argument. Here, when we say the actual value, we actually pass in a pointer that points to the actual value. So in this way, you can set all the necessary arguments for this particular kernel. In our example of matrix multiplication, we actually need 7 of these arguments to be set up properly. The first argument is the destination buffer or the resulting matrix, which is the buffer C. It's spelled differently here, but you know this should be the buffer C we created. Following that, we have the size of these matrices, A and B, the width and height of these matrices, and then we have the 2 input matrices. Now, one thing you have to be very careful is when you initialize multiple kernel arguments, you have to make sure these indices of these arguments are set up properly. Oftentimes, when you do copy paste of this line to set up another argument, you forgot to change the indices here, and that causes some problems that you will be encountering when you execute the kernels. Next step in running the kernel, well, before we actually run it, we have to set a local and global workgroup size. This is where we specify the number of work items in a group and also the number of work groups. In this example, we're choosing to use two-dimensional compute domain. And the way we set up this is that in each work group, we want to have 16 work items. As we see here, this is the local workgroup size. For dimension 0, we want to have 16 work items. And for dimension 1, we also want 16 work items. And for global workgroup size, we also have two dimensions here. We're going to say we want to have WC these many work items in the 0 dimension, and also for the 1 dimension, we have HC these many work items for the global size. Once we have these kernel arguments and the local workgroup size and global workgroup size set up properly, we can now execute the kernel. We'll call this OpenCL API CL enqueue ND range kernel to instantiate the kernels. The first argument is the command queue, and the second argument is the kernel object that you created. And we're going to specify how many dimensions we want to use, and this optionally you can choose the work item global offset, which we often leave just now. And for the next two arguments, we're going to specify the global work group size and local work group size. The final three arguments to this CL enqueue ND range kernel call are related to events. Essentially, in this example, we don't have any events that we're going to wait for, and will not generate any events from this kernel execution. And we will talk more about events and how we can use them in the later lectures. The final step in this OpenCL program is to obtain results after the kernel execution is completed. We will use this CL enqueue read buffer to read results back from the device to the host memory. At this point, we assume that the kernel execution has completed. So in this read buffer API, we will use the command queue, and we'll use the output buffer, and we will use the CL true to indicate the synchronization requirements, which means that we want to be able to this call will not return until the read is complete. And we'll indicate the size of the buffer and the pointer to the host memory where we want to read the results to. The last three arguments in this API call are again related to events. In this example, we are indicating we're not waiting for any events, and also this API call will not generate any events. And we'll talk more about events in future lectures.